Thank you. So I can start now or
yes,
no?
please.
Yeah,
thanks.
Okay, good afternoon, everyone. My name is Hanwei Yu.
Sorry, Hanwei, just for the record, Hanwei has asked for her presentation to be recorded, so I'm going to record her presentation.
Yeah, so can you please record it now?
Yeah.
Okay, thank you so much.
Recording in progress.
All right, thank you.
Okay, good afternoon, everyone. My name is Hanwei Yu, and it is my pleasure to present my progress of my first year PhD work and report my whole PhD study blueprint. The topic of my PhD study is lithium recovery from brine using emerging capacitive deionization. Before starting my presentation, I would like to thank my supervisors, Professor Sheng, Guthrie, and Chao He, for their support on my PhD study. In today's presentation, I will begin with the background of lithium recovery and a literature review of CDI technology. And then I will show the research gaps and objectives of my PhD study. After that, I will try to highlight my current study on MOF-based MCDI for selective lithium extraction from binary simulated brines and talk about the challenge and the future work. Finally, I will finish my presentation after presenting the publications in the past year and the mandatory ethnic work. So first, why we need to recover lithium from brines. So as one of the most crucial metal elements nowadays, lithium is widely used in various important industries such as batteries, ceramics, and lubricating greases. Let's have a look at the global demand of lithium nowadays. In the past decades, the demand of the consumption of lithium boomed from 24.5 kilotons in 2010 and to 93 kilotons in 2021. So it really challenged the supply from the conventional ore resources. On the other hand, lithium is abundant in aqueous resources. About 75% of lithium on land is stored in brines, and the reserve in the ocean is even over 60,000 than that on land. As a result, especially for Australia, a lithium-rich country, it is very significant to develop technologies for recovering lithium from aqueous resources. So far, the conventional methods to extract lithium include evaporation and precipitation method, solvent extraction method, and absorption method. The widely used evaporation and precipitation method takes advantage of solar energy and wind in some large open-air shallow evaporation ponds to concentrate the lithium-rich brine at first. And then by adding some precipitants, the lithium compound can be produced. In the solvent extraction and absorption method utilize the chelating agents and the lithium absorbents to selectively extract lithium from multi-ion brines. The most widely studied lithium absorbent is mantle-based lithium-ion sieves and mantle organic frameworks. Except for these mature technologies, there are also some emerging methods based on electrochemical methods and membrane-based methods, such as electrodialysis, capacitive deionization, nanofiltration, and membrane distillation crystallization. So let's have a look at the pros and cons of these technologies. The evaporation and precipitation method shows a merit of high technology maturity and low material costs. But the processing is complex and time-consuming. The solvent extraction method uses simple equipment and operation to produce lithium product with high purity, but it is not sustainable since the organic solvent can corrode the equipment and the organic solvent leakage can pollute the environment. The absorption method shows advantages of high lithium selectivity and simple operation process. But the changeable structure of some absorbent can reduce the stability and limit the application life. The electrochemical method can extract the lithium very fast, but the operation cost is high. The membrane-based method shows the merit of high energy efficiency and low environmental impact, but it is not inexpensive, and the membrane stability problem can limit the application sometimes. Now I would like to have a literature review of CDI technology. Here we can see the history of CDI development. The concept of CDI was first proposed in 1960s. The breakthrough development in the 20th century include the invention of flow-by CDI and the flow-through CDI. And in the 21st century now, more and more CDI cell architectures are proposed, including membrane CDI, flow electrode CDI, hybrid CDI, and inverted CDI. So how does CDI system work? With the assistance of the external electric field, cations and anions move towards the oppositely charged electrode under a very low voltage. The porous carbon electrode can temporarily absorb these ions, and then by applying a reverse charge, these ions can be released into the solution. The potential applications of CDI include seawater desalination, energy harvesting, water purification, and resource recovery. And the advantages of CDI include technical simplicity, inexpensive cost, mild operation conditions, low energy input, and high energy efficiency. So the core research topic in this field involved electrode modification, operation optimization, cell structure design, and application development. So in the field of CDI for lithium extraction, most studies focus on the material synthesis and electrode fabrication. For example, some manganese-based lithium-ion sieves were used as a cathode for CDI cells. Also, there are some research focused on the process enhancement, comparing and combining different working electric modes, including constant current, constant voltage, zero current, zero voltage, zero charge voltage, reversed constant current, and reversed constant voltage. Here I summarize the papers on CDI-based lithium extraction. The studies of the cell architectures are focusing on flow-by CDI, MCDI, FCDI, and HCDI. And the popular electrode materials are carbon materials and manganese oxides. And the applied voltages are usually within 2 volts. And the source solutions include the simulated brines and the natural brines. After doing the literature review, I would like to share my perspective of knowledge gaps regarding in this field. From the aspect of electrode development, metal-based lithium absorbents could be promising new electrode material since they have shown excellent lithium selectivity and capacity. For MCDI, it is necessary to fabricate uniform, robust, stable, and defect-free membranes. And there's systematic theoretical studies is lacking nowadays, it needs to be further understood the mechanism of ion separation for many advanced membrane materials. And in experimental studies, it should be more clear to investigate the key process parameters of the application environment. And since most of the previous studies are focusing on are using simulated brines, so the more natural feed brines should be tested in using CTI. And the lithium recovery experiment with pilot, there's no lithium recovery experiment with pilot scale or large scale CDI facilities. And for the process optimization, modeling can be a useful tool. And for evaluation of the material and process, we should consider the purity of lithium product and the performance of lithium extraction after a long run. And life cycles assessment can be a useful tool in energy consumption and environmental impact calculation for comparison or for CDI and other technologies. And also, there need to be more design of hybrid process combining the advantage of different technologies. And based on some of the knowledge gaps, here are the research objectives and the planned projects of my PhD studies. I would like to use my project 1 to analyze the ion selectivity mechanism of the electrode modifier through CDI's experiments, and use the project 2 and 3 to synthesize some new memories with nanopores for selective lithium extraction from brines, and to investigate the effect of operation conditions in CDI systems. And the project 4 is to optimize the process of membrane fabrication and CDI for lithium extraction by modeling. And finally, I would like to design a hybrid process to extract lithium from natural brines or seawater brines, combining the advantage of CDI and other technologies such as absorption or MD. And now I would like to show my present research project. This figure illustrates the concept of my MCDI system. Here, the ZIF8 PDA mixed matrix membrane on the AC electrode plays a role of filters. When applying a low voltage to the system, the cations can move towards the cathode. But the ions with large sizes can be blocked by the membrane. Only lithium ions can pass through and temporarily stay in the porous carbon electrode. These ions can be dissolved after applying a reverse voltage. So why I choose MOF? According to a simulation study published on the Science Advances, some MOFs with sub-nano channels, such as ZIF8, have the property of ion selectivity due to the size-sieving effect. Specifically speaking, the lithium and the competing cations become dehydrated when entering the ZIF8 framework, and then rehydrated when they exist. because the hydrated ionic diameters of these cations are larger than the window diameters of ZIF8. But the dehydrated ion diameters are smaller than it. However, the ion transport rate of different cations are different. Compared to other cations, the dehydrated lithium ions can pass through ZIF8 first, thus realizing the lithium separation. But the ZIF8 has low water stability, so I use dopamine and synthesize the ZIF8 polydopamine mixed matrix membrane to enhance the water stability. So here is the schematic of the electrode. And my modified cathode is a ZIF8 polydopamine coated activated carbon cathode. And a bare AC cathode and commercial cation exchange membrane coated AC electrodes are selected as the control. So here is the electrode preparation process. And I used 1,280 of zinc and 2 methylene methazole in methanol for 72 hours at room temperature. And then by adding dopamine into ZIF8 seeding solution and store for 12 hours, the ZIF8 polydopamine can be synthesized. After that, I use an in situ growth method to coat ZIF8 polydopamine membrane on the activated carbon electrode. And here is an example of the modified electrode. And here is the CDI test design. And the CDI system includes a CDI cell, DC power, a computer, conductivity and pH meters, and a pump and a feeding solution. My feeding solution is equimolar binary models, including lithium and another competing ions. The competing ions are sodium, magnesium, potassium, and calcium. These experiments are based on all the 3 electrodes, and the additional test only for the modified electrode are the CDI test using binary field brine under the voltage of 0.5 volts, and the CDI test using only single component brine and the 5 components feed solution under the voltage of 1 volt. So here are the CDI performance metrics: the ion removed rate, the relative ion selectivity,